mucous matters.
So thanks to the organizers and to the ICTS team for their always excellent hospitality. So I'm Jason, I'm at IIT Bombay, and today I'll talk about mucous matters, pun intended. And specifically, I look at aerosol entrapments inside pulmonary airways. So as we were all made acutely aware a few years ago, that when we inhale air, we bring along a whole bunch of particles. And even if you don't have pathogens, you have allergens like dust and pollen and so on. So if these particles make it past your nasal cavity and through your trachea, they would then enter the branching lung network, which goes down 24 generations. And along the way, you will have a situation that looks like this. So you will have aerosols in the air, right? And you have oscillatory respiratory airflow as you breathe. And then you have the epithelia of the pulmonary airway. And the point is, if these allergens reach the airway cells, then they can create all kinds of issues. And so the basic defense mechanism is this mucus coating. So you can think of it like a tube, and on the inner wall of the tube, you have this mucus. And what I want to look at today is how these particles can get entrapped by the mucus, or on the other hand, avoid the mucus and reach the epithelium. So this work is being done by Swarnitya, who's a PhD student at IIT Bombay. And I'm grateful for funding by SERB, IITB, and CEFIPRA project, along with Dario, Jeremy, and Shamriti. All right, so just a brief background about the setup and then how we're going to model it. So if you look at the airway wall and you zoom into the wall, you'll have these epithelial cells, and then you have the mucus layer above the cells. And in between, the mucus layer really rests on what's called the periciliary liquid. So it's like a watery liquid, much less viscous than the mucus. And inside that liquid, you have the cilia. So these are hair-like filaments which actively beat in a cyclic manner. And the filaments themselves self-synchronize in an interesting way. So that in the end, you have a kind of carpet of motion that propels the mucus forward. A way of thinking about it is you have, it's like you're rowing a boat, right? The rower makes a cyclic motion, but you dip the oars into the water only in the forward stroke. And as a result, the boat just moves forward. So the inverse happens here. The tips of the cilia penetrate the mucus only in the forward stroke. This is a cartoon, but this is an actual image of this system. And so you can see the cilia there and the mucus layer, deformed mucus layer sitting on top of it. This is how the cilia typically kind of rotates about its base. So it has a upright forward stroke that pushes the mucus forward, and then when it retracts entirely within the liquid watery PCI. And that's another image of, this is actually a rabbit trachea, but it shows that you really have this kind of carpet that propels the mucus forward. Okay, so that's the sort of site of our study. And of course, as I had mentioned, the reason that we're interested in this is because when you inhale these pathogens, if they reach the wall, or even allergens, they can trigger inflammations of various kinds, which can constrict the airway. They can also cause oversecretion of mucus, which can mean that this mucus will accumulate and form plugs that cause respiratory problems. And what we're going to look at today is that, of course, the lungs are very complicated. You have the nasal cavity, you have the terminal alveoli where the gas exchange happens with the blood. But I'll focus on the intermediate airways for a couple of reasons. One, these are relatively small, so they're easy to get plugged. And also the airflow here is rather weak because they are small, right? So the Reynolds numbers are of order 1, order 10. So the airflow is not strong enough to propel the mucus out. Unless even when you cough, it may not be the case. Whereas in the upper airways, of course, when you cough, it can actually rip off the mucus. And that was the whole problem about ejecting mucus and spreading disease. So we look at these intermediate cases. All right, so let me talk about the 3 key fluid mechanical non-equilibrium processes that control what's going on here. So one is the distribution of mucus, right? So ideally you would like the mucus to be well distributed across the airway so that it can trap particles. And we'll see that that is governed by surface tension driven film dynamics, which is a well-studied pattern formation topic. Then you have the transport of the film by cilia and how that can be modeled. And finally, you have the transport, which can be Brownian for small particles, but non-Brownian and inertial for larger particles. And that will control where the particles go, whether they reach the wall or the mucus. And yeah, these are some basic properties just to convey the multi-scale nature of the problem. So for example, if you look at length scales, The airway length is typically a few mm. The airways that I'm looking at, the 10th to 15th generation. Whereas we look at the cilia, they are 7 micrometers or so, right? Very small. And then the layer of mucus is also about 5 micrometers. So you really have you have a thin film that is now spanning several thousand heights that you would like to describe mathematically. Okay, so let's do it, just an introduction to those 3 important transport processes. So the first is film dynamics. So when you have a thin film in a cylindrical configuration, either as a jet or on the outside of a rod, or in this case on the inner side of a cylinder, it suffers an instability driven by surface tension, which since it's an Indo-French workshop, I shall refer to as the plateau-Rayleigh instability. So basically, if you have a cylindrical interface, it deforms and forms beads. So I'll show you an example here from a kitchen experiment. So it's a glass of chocolate milk and I have a whisk in it. So you will notice that when the whisk is drawn out, initially it's uniformly coated, but then very quickly you spontaneously develop little beads. So that is surface tension pulling the liquid into these small droplets. And what you notice is that there is roughly a ordering. There's a nice length scale that appears, which is essentially the fastest growing wavelength of this plateau-Rayleigh instability. So it very quickly forms, and roughly there is a reasonable spacing between these things. So that's the sort of instability that would happen in reverse on the inner side of the tube. And so you can imagine if the mucus gathers itself into these little humps, if they are big enough, they could occlude the airway. So that's one aspect of the problem. Yeah, so the basic idea is if you have this tube and you have a small perturbation, because of the Young-Laplace pressure difference, you have a pressure decrease in this hump, which will pull more fluid into that hump. And the exact growth of this instability, whether it grows or decays, depends on the wavelength. So that gives you the droplet size. Now, this problem itself has, you can look for equilibrium solutions by looking for solutions of the interface that have uniform mean curvature. And it turns out, as shown by Everett and Haynes in the 70s, that if you have a lot of liquid volume, then you have this sort of liquid bridge forming. So the film has no stable configuration. The moment you perturb it, it gathers into these humps, which are so big that they pinch off and you get a liquid bridge. So you get something like this. And then there are, at capillary timescales, you have a recoil. And that actually can damage the airway walls, which has been shown by Grotberg's group and others. And if you're in the terminal airways, very close to the alveoli, this especially happens in small children, the pressure differences are so large that it can collapse the airway. But today I won't look at that. I'll look at low volume cases. And there's a critical cutoff beyond which these solutions no longer exist. But if you're below that cutoff, you do get stable solutions, which have been called anduloids. They're like humps, but remember they're annular because you're looking at a tube. So it's like a collar of liquid, which is now stable. So it's stable because it's balancing the longitudinal surface tension with the radial surface tension or circumferential surface tension. So this is a simulation, which I will discuss later, how it's done. But you see, there's a film, it deforms into these nice unduloid-shaped things, and things are stable, so it doesn't occlude. Now, what's interesting here is if you now think about particles, you'll see that there are these humps, but there are also these zones where mucus gets depleted because it gets drawn into the humps. So these are places where particles can directly reach the airway wall. And this is a situation that is unavoidable. The moment you put a film, it will form these humps. Right? So that's interesting, and we will, the extent of these zones is going to be important. Okay, quickly look at mucociliary transport. So there have been many models of describing how cilia propels the mucus. There are early models, pioneering work by Blake, where he takes these cilia shapes and treats each cilium like a thread of Stokes slits, and he's able to get the mean mucociliary propulsion. Today, there are much more advanced models with immersed boundary methods and so on, so you can get things like how the mucus interface deflects. But these are quite complex, and as you can see, you can do maybe a few hundred cilia, but we need to do this across very large lengths across the airway. So then it's expedient to treat the effect of the mucus via a wall boundary condition. So this has been done quite recently by several people. So you basically take the mucus layer, and at its base you apply a boundary condition that mimics the action of the cilia. And that just gives you the main effect, which is to transport the mucus. And you can derive this boundary condition to varying degrees of rigor. And Brato here at ICTS is working on these related problems. So we'll take a relatively simple form of this that has been used in recent work. Okay, let's do the third thing now, which is the particle transport. So the total deposition in the lungs has been measured experimentally. Right? So you put a person in a sealed room, you inject a known amount of aerosol, and then you measure how the amount of aerosol changes after maybe an hour or half an hour of breathing. And so you actually have this interesting behavior, which the key thing to note is that it non-monotonically depends on the particle size. So your aerosols you have from like 0.01 microns to about 10, 20 microns. And you can see that the extent of deposition, so how much of it stays in the lung, is actually non-monotonic. It's not difficult to understand because the very tiny particles, sub-micron, are Brownian. So when they come in, they are diffusing all over the place very rapidly, so they just go to the wall and get stuck on the mucus or on the wall. As you increase the particle size, the Brownian strength reduces. You get things which are more like tracers, so they don't deposit as quickly. And what's interesting is when you go to larger sizes, you again get a recovery of this amount of trapping or deposition. And the mechanism here is because the particles are non-Brownian now, but they have enough mass and density to deviate from streamlines. This is actually what Rama spoke about the other day in the context of cloud droplets. So if the particles are heavy, they don't follow the fluid velocity exactly, you can model them with the simplified Maxi-Riley. And then in a turbulent flow, for example, where there are nice vortices, the particles get thrown out of vortices, right? So they don't follow the streamline. And in the lungs, something similar we will see happens, that as the flow goes past those mucus humps and goes into the airway, the same kind of forces can throw the particles onto the wall. So this sort of dissipative dynamics has been explored and in great detail by Jeremy also, and by Rama and her students. So these are the questions that we want to answer broadly in this work. So one is, what is the effect of this mucus distribution of humps and depleted zones, right? And how does it affect particle trapping? One basic question is more mucus better? Right? So you'd think naively that if I need to trap particles, there should be more mucus, but we shall see whether things are as obvious. And then how do these answers change with the size of the particle, because the mechanisms change from Brownian to non-Brown. All right, so this is the mathematical model that we'll be using. So as I had mentioned, we model this in a simple way as a cylindrical tube, so that's a center line. And we have a layer of mucus, Newtonian mucus and Newtonian air. And at the wall, we apply the Celia boundary condition to mimic this transport. So we have the Navier-Stokes for both phases. We apply an oscillatory pressure gradient in the air to mimic breathing. And we apply the usual boundary conditions at the interface with this Celia forcing condition at the wall. I'll skip the details, but basically we put a velocity that's like a traveling wave and which is asymmetric. So the forward stroke is stronger than the reverse stroke. So it creates a propulsion that sort of moves 2 steps forward, 1 step back, and you eventually get motion. What we will do is, rather than solve the full equations, we'll use a thin film version of these equations, which is a kind of averaging based on a technique developed by Georg and Christian. And it's really quite a remarkable technique. So this is an example of falling liquid film with airflow above it. And this is a direct numerical simulation of the Navier-Stokes equations. And this is the reduced model developed by Georg and Christian, and you can see the remarkable agreement. Physically, it's based on the fact that because the film is thin, the relaxation timescale for the cross viscous stress diffusion is much faster than the dynamics you want to study along the length. And mathematically, the problem has a center manifold corresponding to solutions that have flat interfaces. So you can do a center manifold reduction, something in that spirit. So these are the equations. They look quite messy, but it can be done, and then you can do these simulations, which have been verified with DNS. And what we will do is I'll quickly take you through some features of the flow and then look at what the implications are for particles. Okay, so on the top, here are 2 snapshots of the evolution of this film on my computational domain. So on top you have cilia, bottom there's no cilia. In both cases you see this plateau Rayleigh instability draws the mucus into a hump with depleted zones. And it seems like the cilia has no effect other than to just translate this hump. If I look at the minimum thickness versus time, again we can see that the cilia doesn't have much of an effect. And it's not surprising because the cilia force is not acting transversely, it's just propelling things along the air. In this space-time plot, it again just reinforces it, that there's a hump and that hump simply translates with this mean propulsion speed. So really the cilia is important once the particles are trapped, because it evacuates the mucus out of the lung system into the digestive system. But for the actual trapping of particles, they are not important because the transport is very slow compared to the airflow and the mucus dynamics. Okay, let's consider air quickly. So because the viscosity and density of air is so much less than the mucus, you can sort of effectively decouple the problems to leading order. Right? So the air sees the mucus as a kind of deformed wall, and its flow doesn't get affected by the mucus other than the fact that it has a contoured channel to pass through. So these are some snapshots of the flow. So that's the mucus bulge at some long time state as it's moving. And this is the airflow, and these are streamlines. So in the full model, you can see the air just gets deflected by the mucus. There is a kind of vortical structure in the mucus, but the velocities are much lower. So on the same, scaled in the same way, you can see this is order 1, whereas the air is some order 3 times greater. So the air is really super fast compared to the moving mucus. And you can, if you look at the decoupled model where I solve the mucus and air separately, which is easier to do, you see the mucus has some differences, but the air streamlines are basically the same. So for the purpose of this study, we can use a simpler model and just calculate the air. There are some interesting dynamics. I won't spend too much time, but in these cases where some complex circulations arise, these are very short-lived. So if I'm interested in where the particle is moving, I don't really have to worry about these cases, and most of the motion is going to be relatively simple. The only thing of interest is, as the air moves past the hump, you see that there are these curved streamlines. And this is where you will see inertial particles can get thrown out. Okay, so yes, the one important question was how does the amount of mucus affect things? So here we'll see how it affects the extent of these depleted zones. So here are some simulations. If I take a lot of mucus, it eventually, these will form bulges that will go and pinch off. Okay, so I've not shown the full thing, but if we continue the simulation, this will simply hit the center line, which means you'll get a liquid bridge. So that's a case that is not, we will not look at here. If you have low amounts of mucus, you get those stable unduloids. But in an intermediate region, things get interesting, as you'll see. So here are a couple of randomly initialized simulations. Everything is the same. And you can see some interesting sliding dynamics that in one case saturates, but in the other case, again, I'm not continuing the simulation, but if I do, it will go and pinch off at the wall. So what you have is a situation that is initial condition dependent, which is not surprising in these instabilities. These kind of sliding based dynamics was explained a few years ago by us with Georg and Ranga. Okay, so because of the stochastic nature of, there is dependence on initial conditions, we do many simulations on long domains with random initial conditions. And what we find is that we can measure the closure fraction, so the number of cases which stay closed, which close, and how many open. And you can see that it decreases as the, this is the thickness of the mucus film, from 1. So these are thinner films. So as you make the film thinner, the chances of them occluding get less and less. And so for the non-occluded cases, we can calculate the dry out fraction. And this is the first interesting result. So you see that the width of those depleted zones, which are exposed to particles, they actually grow as the mucus increases. So when I go from right to left, I'm increasing the amount of mucus. And naively, you would think you would get better coverage. But actually, you have more dry out zone. So in the interest of, we can explain that by a theory. Actually, this curve is the theory. I'll not go into the details except to say that it's based on the idea that if you have an interfacial instability subject to random perturbations, the perturbation that dominates is the one with the fastest linear growth. And this was propounded by Rayleigh way back on, in his paper on, in fact, the plateau-Rayleigh instability. And a demonstration is shown here. If in the plateau-Rayleigh instability, if you look at the linear instability, you will have a dispersion curve like this. And you have modes of different growth rate. So the peak mode looks like this, and this other mode is half harmonic. And if I do simulations perturbed with these different initial conditions, you will see no difference. So really, these instabilities are very robust to initial conditions. In most cases, you can tend to get dominated by the fastest mode. So we use that idea to base our analysis on just one periodic mode with the fastest growing wavelength. And then we can, of course, calculate this dry out region and its effect with mucus. So that's what I showed you as the line in the previous. Okay, let's move on to particles. So because I want to treat a range of particles going from tiny Brownian particles to inertial particles, I'll solve that simplified Maxi-Rayleigh, but now as an SD augmented with Brownian forces. And we take particles going from sub-micron to about 50 microns. So the Peclet number, which small Peclet number means more Brownian, spans several orders of magnitude. And for the same case, the Stokes number grows. So the inertial effects grow with particle size and Brownian effects decrease. So the heart of the message is in these two movies. So the left one is a diffusive case, small particles, and the right are bigger guys which have inertia. And you can see the big particles get centrifuged out to the core, but you have some of them in a sort of dead zone at the bottom. Whereas the small particles more or less follow the flow, but they have some Brownian motion that will cause them to keep trapping at the wall. You see on the right, as you breathe back and forth, the particles get pushed to the center line, but there is some amount of ballistic trapping in the hump. And the diffusive case, it more or less follows, but it slowly accumulates at the wall. So if I now do those simulations for about, I can do this for different times, but let's say 30 seconds of breathing, half a minute, and look at the amount of trapping versus the particle size, you get the same non-monotonic behavior that has been measured experimentally for total lung deposition. But this is just in a single airway. And things here are Brownian, so then they decrease as the particle size increases. But at the largest sizes, you get that inertial effect. And this effect is because there is a mucus hump which is deep, so that causes the streamlines to bend. So if I reduce the amount of mucus, that effect is lost, you see. So you don't have that inertial-driven trapping. Okay, so this was one important question, that if I have more mucus in the airway, will I trap more particles? And we already saw that having more mucus actually exposes more of the wall to infection. So when we actually do the particle trapping, we see that if you look here on the amount of particles trapped at the wall, the solid line is the more mucus case. And we see that you actually have more particles reaching the wall. That's because of this exposed depleted zone. So it's actually counterintuitive, and what's ideal is to have a thin film of mucus that can be uniformly. Okay. Then we can ask whether these whether the trapping here at largest particles is actually due to that inertial effect. So if I measure the velocity at the point of trapping, which is like a collision velocity, and plotted versus diameter, the smallest particles collide rapidly because they are diffusive. Then it goes very low, so these are almost just grazing collisions. But again, the largest particles have an uptick in the collision velocity, and that shows you that they're really getting thrown at the mucus hump. Okay, I'll skip this last point. So let me conclude with this. So we found some interesting results already. The first counterintuitive thing is if you actually have more mucus, you actually leave larger sections of the wall exposed because of the surface tension driven Rayleigh plateau. And because you have more regions exposed, you can have more trapping. There are more particles reach the wall. But we also saw that the deep particles can intercept large particles, which is good because then they don't go deeper into your lungs. So there are some trade-offs, as one might expect. And this is just the beginning. There are many interesting things that can be done with this setup. So one example is you could ask if the particle is an allergen and it reaches the wall, it would then secrete mucus or cause mucus to be secreted as a defense mechanism. So you can imagine particles coming in, depositing on the wall, initiating secretion that could cause blockage. And in fact, that is a mechanism postulated for fatal asthma, where very rapidly you can have asphyxiation. Yes. So with that, I thank you for your attention. I'm happy to take questions.
Yeah, thank you. Questions?
When you showed the inertial particles in mucus hump, you showed most of the particles go to the central line.
Yes.
But in channel flow, like people have found that there is a specific number close to the wall that inertial particles do aggregate in a turbulent channel flow. Like, is that broken in this case?
So there are many transport mechanisms depending on the regime.
Right.
So in turbulence, of course, things will be different. Right? So here the flow is laminar.
I see. Okay.
And the particles are very tiny point particles.
Right.
Right. So the main thing is it pushes it down, but before it can do that, the particles also collide with that hump, just because they are deviating from streamlines.
Yeah. Right. Thanks.
Okay. I have a simple question. So if you do this simulation in 3D versus 2D, I mean, does the result same or conclusions?
Yeah. So it is 3D, but axisymmetric.
Okay.
And the particle motion is 3D.
Okay.
Yeah. So it's like a 3D tube. Okay. The only assumption is the film is a axisymmetric film. And then the particle motion is 3D.
Okay. Yeah. Okay, so if there's no question, let's thank the speaker
you.
again.